Welcome back, dear students. So in this we are going to introduce a new concept in this module, that is the air standard cycle. So already you have studied the working of petrol engine, diesel engine, etc. So what is the importance of this air standard cycle? So the question is, how will you find out the performance analysis of an engine? For example, how will you find the efficiency of an engine? Normally it will be by experimental investigation. So you will have a particular engine, you will run the engine, measure the values, input and output, and you will get the efficiency. But in all the cases it is not possible, or it may be not possible to conduct such experimental study. So we have to go for some theoretical equations. This is same in most of the engineering system. All the case we cannot go for experimental study, so we have to go for some theoretical investigation also. And in the case of engine, this theoretical investigation is known as the air standard cycle. So in every theoretical investigation it is followed by certain assumptions, because otherwise it will be very complicated. Mathematically it will be difficult to solve such systems. So we have to follow certain assumptions so that we can simplify our system and we can easily get into an expression. So here also we have certain assumptions, so we have to study what are the assumptions for air standard cycle. So first assumption is, in air standard cycle the working fluid is considered as dry air, which is also considered as an ideal gas, So this is very important, this assumption. Actually we know in an actual engine what will be the working fluid. It will be a mixture of air and fuel. If it is a petrol engine, it will be a mixture of petrol and air, and if it is a diesel engine, it will be diesel and air. But if you are considering that for theoretical derivation, we will be very difficult, because the properties of fuel also we have to consider, so it will be a very tedious job. So what first assumption in air standard cycle is, our working fluid here is, we are neglecting fuel and we are considering as only dry air, and again it is considered as an ideal gas. The advantage of ideal gas is we can use the ideal gas equation, that is PV equal to MRT, or PV by T is a constant. Remember, in thermodynamics we will be using PV equal to MRT, not PV equal to nRT. You might have studied in chemistry this ideal gas equation, PV equal to nRT, but this is for chemistry. In thermodynamics we are considering systems with equilibrium, in chemical equilibrium, so more than number of moles we will be using the mass. And here the R is or we can say R bar. Here the R is ideal gas constant. Remember, in chemistry we are using PV equal to nRT. Here the R value is the ideal gas constant, 8.314. but thermodynamics and in engineering we will be using mostly this equation, PV equal to MRT, where M is the mass of the gas present, and this R is different from universal gas. This is characteristics gas constant, so it is different for different gas. Air, it is having one value, some other gas it will have different value, so remember this. So we are following this assumption, our working fluid is dry air, which is also considered as an ideal gas. But in actual engine this is not the case. Our working fluid will be air plus fuel mixture, and it will be not an ideal gas, it will be a real gas. Now second assumption is, system is considered as a closed system. This is also very important. System is considered as a closed system. But what about an actual IC engine? In an actual IC engine, our system will be open system because air will be entering, fresh air will be entering, we will produce work and the exhaust is emitted. So it is an open system, batch like system, open. But in this particular derivation we are considering our system as a closed system. That means there will be no mass transfer between the system and surrounding. Only energy can transfer in terms of heat and work. So that is another important assumption. And third assumption is connected to this. Since our system is closed system, the heat, how we are adding heat. So we have to add heat by an external source, a constant temperature external source. But in actual engine we know that heat is generated by burning fuel inside an IC engine. But since our system is a closed system and also we are considering only air, the heat must be added externally. So heat is added externally with the help of a or from a constant temperature source, from a constant temperature, high temperature source. So this is a thermal energy reservoir. Source temperature will not change by giving a finite amount of heat, just like a furnace, etc. And similarly we have fourth assumption, that is heat rejection also like this. Heat is rejected to a low temperature sink outside the system. So heat addition and heat rejection is to an outside externally with the help of a high temperature source and a low temperature sink. And another assumption is here all the processes are considered to be reversible. All the processes are reversible, but we know that in actual conditions most of the process will be reversible, and there will be no heat loss or frictional loss. That is another assumption. There will be no heat loss or frictional loss. So if in an actual engine there will be a lot of frictional loss to the piston, moving parts, etc. But in this derivation we are neglecting all that for the sake of simplicity. And finally the physical constants. So what are the physical constants? Physical constants means specific heat, Cp, Cv, gamma, etc. All these constants will not change in the entire cycle. Will not change. That is, for particular cycle we will have one Cp value and one Cv value. But in actual case that is not the case. As temperature increases, the Cp and Cv value will change. Remember, IC engine we have a wide range of temperature. In suction stroke the room air or the room air fuel mixture is entering, but after combustion this will be very high temperature, 1500 or around that. So in that temperature range actually this value will be different for different process, but for this derivation we are assuming this as a constant. So these are the important assumptions we have to keep in mind while deriving air standard efficiency. And we have to study in this syllabus, we have to study 3 air standards efficiency. Derivation of air standard efficiency we have to study the 3. One is Carnot. So first one you have to study is Carnot cycle, that is the hypothetical cycle which will give maximum efficiency between two temperatures. Then we have to study Otto cycle, which is the working cycle of petrol engine, and diesel cycle, which is the working cycle of diesel engine. So these 3 cycles we have to study. So all these cycles you have to keep in mind this assumption. So you can write this assumption if the derivation is asked, even an Otto cycle or diesel cycle you can write this assumption. So in this first one and this first 3 and 4 are very very important. Up to this very very important assumptions. So thank you.